So next topic on this lesson is Ampere's circuital law. Ampere's circuital law. Supposing there's a current carrying wire, you know that it will produce a magnetic field around it. So the direction of the magnetic field according to right hand screw rule or right hand thumb rule is like this. So the wire, can you see the wires piercing through the center? And so the magnetic field around it is in this direction. So the magnetic field at this point is in this direction. So supposing there is an element of length dl, or along the circular path it is dl. So the Ampere's circuital law states that integration of B dot dl is equal to mu naught into I. This is when you can recall in electrostatics you would have done Gauss's law, which is integration of E dot ds is equal to q by epsilon naught. Instead of 1 by epsilon naught is mu naught, instead of q it is I, and instead of ds, that's a surface integral of electric field over a closed surface, but this is line integral of a magnetic field. Line integral of a magnetic field over a closed surface. Closed surface, over a closed loop, The line integral dl, the line integral of magnetic field over a closed loop is equal to mu naught times the current. So that's how you define it too. Ampere's circuital law states that the line integral of the magnetic field around any closed circuit, is equal to mu naught times, that is permeability times total current flowing through the closed loop. Okay, so that's all. That's the definition of Ampere's circuital law. So how do you define it? The line integral of magnetic field around any closed loop is equal to mu naught times, that is permeability times the current flowing through the loop. Current flowing through the loop. So that is the definition for Ampere's circuital law. What the applications of Ampere's circuital law is to find the magnetic field due to a solenoid, or inside a solenoid. Okay, magnetic field inside a solenoid or outside a solenoid or due to a solenoid. Okay, so let's first consider a solenoid here. Solenoid is consisting of many turns of coil. Yeah, this is solenoid which is cylindrically wound. A current I is flowing through this solenoid. Now consider a closed loop A, B, C, D, and according to which, according to the Ampere's circuital law, it's integration of A to D, A to B, B dot dl, plus integration of B to C, B dot dl, plus integration of C to D, B dot dl, plus integration of D to A, B dot dl is equal to mu naught times the current. But I won't write current as I, because there are total turns of the solenoid is capital N. Total turns of the solenoid. And so though I is the current that's passing through, there are N turns. At any instant there will be Ni will be the total current. So mu naught into capital N into I. So then let's look at this. You should know that for a BC, it's B dot dl. That is magnetic field and the dl element. Cos theta is the angle between. This is dot product. It will be cos 90. It will be cos 90, so the answer will be 0. So can you imagine for the side BC, I'm just doing a color for you. The magnetic field direction is within the bar magnet, within the solenoid. Say for example, it's going to be uniform and it's going to be like this. So the magnetic field is perpendicular to BC and therefore it is 0. Similarly, AD will also be 0 because of cos 90 is 0. BDL cos 90 is 0. What about CD? This is 0, but for a different reason. Why? Because CD is above the solenoid. The solenoid is like more or less like a bar magnet. So if you see above, there is no magnetic field. The attraction happens only at the poles. So you can say B is equal to 0 here. Even though some field lines will pass through, yes, but there will be few field lines. The field lines density is very less. So you can consider that the magnetic field B is 0 above the solenoid. So above the solenoid, B is equal to 0, and hence this whole thing becomes 0. So the only thing which is left for us is integration of A to B, B dot dl is equal to mu naught into n into I, where B is a constant, take it out, A to B is the whole length. Can you see the length of the solenoid, we can say. So integration of dl is equal to mu naught into n into I, and integration of dl is L. Integrated from upper limit to lower limit, let's say L is the length of the solenoid, total length of the solenoid. B into L is equal to mu naught into n into I. So B is equal to mu naught into capital N by capital L by I. The total number of turns is capital N by total length is capital L, and which will get you small n, the number of turns per unit length, number of turns per unit length. The total length of the total turns by total length will give you the number of turns per unit length, small n, and therefore you can replace this as small n. So B is equal to mu naught into small n into I. Very, very important formula, mu naught into small n into I. Thus you found the magnetic field due to a solenoid using Ampere's circuital law. That is one application. Next is for a toroid. It's called toroidal solenoid or a toroid. How is the toroid? It's going to be like a slinky, closely wound, but in a like closely wound like this, like a slinky connected together. So if you see, there will be magnetic field within this closely wound place, because current will be flowing through, and that will produce a magnetic field. There will be a magnetic field here. There will be a magnetic field here. So there will be magnetic field lines within the closely wound space, but to the interior free space there will be no magnetic field. B will be 0. To the exterior of it, B will be 0, because there is no current flowing through in this region. So then therefore you understand that the magnetic field exists only on the within the core of the turns. So let's do Ampere's circuital law for this. Is the radius of this is R. Okay, the entire perimeter. Okay, so integration of B dot dl is equal to mu naught into capital N into I again, because the capital N is the total number of turns. B can be taken out. Integration of dl, integrate from 0 to 2 pi r, the entire perimeter is the length here. So mu naught into capital N into I. So B into integration of dl is L, upper limit minus lower limit is 2 pi r is equal to mu naught into capital N into I. Therefore B is mu naught into capital N by 2 pi r into I. The total turns by total length will give you small n as usual. Here length happens to be the entire perimeter, that's certainly different. So you still get the same as the solenoid, mu naught into small n into I, which is a very, very important formula. That's about the magnetic field of a toroid. Next, what happens? Next is force on a charge in a magnetic field. Force on a moving charge in a magnetic field. Okay, in simple terms, let me explain to you that if there is an x-axis in which the direction of magnetic field exists, and there is a y-axis in which there is an electric field that exists, and there is a z-axis, just leave it like that. Supposing a charged particle q with a velocity v enters into the magnetic field, making an angle theta with the magnetic field, it undergoes deflection. This is the basic thing. You should remember that the charged particle moving in a magnetic field undergoes deflection. And that's given by Fleming's left-hand rule. So a charged particle moving in a magnetic field undergoes deflection. So there's a magnetic field, a charged particle is entering into it, it will automatically undergo deflection. Okay, so what is that? So that which concludes that there is a force. The force responsible is called magnetic Lorentz force. It's called magnetic Lorentz force, L-O-R-E-N-T-Z force. Lorentz. It's called magnetic Lorentz force. And that force is given by, what are the three things that exist here? Can you see? Forget about the electric field. We will not talk about electric field in the case of magnetic Lorentz force. If you are considering a charged particle entering a magnetic field alone, it has undergoing deflection, which is given by a force, Lorentz force, which is Q dot V cross B. Velocity magnetic field and charge. Those are three components which exist, and so it's actually Lorentz force, magnetic Lorentz force is QVB sin theta, in other words, because of a cross product sin theta. Lorentz force is QVB sin theta. Okay, so that the force, there will be a deflection. There will be a deflection produced because of this force, and the direction of the deflection will be given by Fleming's left hand rule. The direction of the deflection given by Fleming's left hand rule. Okay. Now, but there is also an electric field. So there is a force due to electric field, which is E is equal to F by Q. According to electrostatics, F is equal to E into Q. So then the force due to electric field is E into Q. Therefore, the total force here will be electric force plus the magnetic force, which is otherwise called a Lorentz force, magnetic Lorentz force. So it's E into Q plus QVB sin theta. So Q is common, so E plus VB sin theta, or in other words Q E plus B cross B. This total force in general is called a Lorentz force. Lorentz force. So what is the difference between this and this? This is magnetic Lorentz force. Magnetic Lorentz force is purely due to magnetic field. The deflection, the force experienced by a moving charge particle in a purely magnetic field is magnetic Lorentz force. And Lorentz force is the total force experienced by a charge particle that is moving in the presence of electric and magnetic field. That's total force which is given by this. So you must be clear with both of this, okay. So let me tell you a better diagram. If you're good at drawing, you can do this. I'm not very good at it, but I can still show you. Supposing, instead of doing an x, y like this, x-axis, y-axis like this, I'm doing an x-axis and y-axis like this. Can you see an x-axis and a y-axis? You know, as a three-dimensional y-axis like this. Angle between them is 90. You can't see that it's three-dimensional, so it's like this. So a particle, supposing a charged particle Q with a velocity v is moving in this, and you know that there is a magnetic field along this direction, and there is an electric field along this direction. You know, it's basically this is a charged particle, velocity v is here. V cross B, Q dot V cross B indicates that the Lorentz force will be in a direction which is perpendicular to V and B, a cross product of V and B. If you have two vectors, when you cross them, you actually get a vector which is mutually perpendicular to both of these vectors. So the Lorentz force direction will be perpendicular to both of this, that is velocity as well as B. So definitely it will not be in XY plane, it will be in and along the Z axis. That will be the direction of the force. That will be the direction of the force. So you can compare this with your left hand rule if you want. Okay, so I'm trying to draw, okay, the thumb pointing outside, which gives the direction of the deflection, and index finger, which gives you the direction of the magnetic field here, B, which is along the x-axis, and the middle finger, which is along the direction of the electric field or the current. We say it current, okay, and there will be curled fingers inside, of course. So this is how we draw the Fleming's left hand rule. You know, magnetic field is index finger, middle finger is current, and that's the force direction. So Lorentz force, basically. It's a magnetic Lorentz force, direction. So then this is a beautiful diagram which depicts it so beautifully. So if you can do this and explain, well and good. But you should know that the V has to make an angle theta with the magnetic field. So that's when you get the Lorentz force to be QVB sin theta or Q dot V cross B. And if you want to include the electric force also, this is magnetic Lorentz force, you want to include the electric force, it's Q into E plus this, which will give you the total Lorentz force. And the one thing that I would like you to remember is this charged particle which is moving in the presence of electric and magnetic field. Okay, this is going to move in a spiral or helical path. You can just remember this, that you're going to. What happens if theta is 0? You know the Lorentz force is Q dot V cross B, would be sin theta. When theta is 0, case study, when theta is equal to 0, there is no Lorentz force. Which means the particle will go undeflected if theta is equal to 0. The particle is going to enter in this direction, the direction of the magnetic field, the magnetic field's direction. It's going to enter the same direction as the magnetic field. It will go undeviated without any deflection. So theta is equal to 0, no deflection happens. Okay? That's a very, very important MCQ that will come for every exam. What happens to a charged particle which is coming parallel to the magnetic field? It's not going to undergo any deflection. It's going to go straight in its path. So that's about it. So next thing that I want, so you understood what is the Lorentz force and stuff. Okay, so next thing that I want to teach you is work done by the magnetic force. Okay, work done by the magnetic force on a charged particle to 0. You have to prove this. This proof is not very important, but however I am trying to find magnetic force, which is magnetic Lorentz force, which is F is equal to Q dot V cross B. Yes, the work done. What is work done? Okay, this is okay, Q dot V cross B, and the work done by the magnetic force on a charged particle. Okay, what is force into velocity? Let me see. Force is mass into acceleration, velocity is distance by time. Okay. We know power is equal to force into velocity, do we? It's work done. Power is rate at which work is done. Okay, and work done is force into displacement by time. So displacement time is velocity. So force into velocity is invariably is power. Okay, so it's power, yeah. So leave it like that. Just recall I was doing. Okay. Supposing you want to, according to Newton's second law, force is mass into acceleration, which is mass into dv by dt, differentiation of velocity, dv by dt. Okay, so this is force, and supposing I am calculating power, say I am calculating power, power is force into velocity from this. Power is rate at which work is done, w by t, which is force into displacement by time. Displacement by time is velocity, so force into velocity. So which means this will become m into dv by dt into v vector. Yeah. Force is also vector, velocity is also vector. Dot product of them will give you a power which is only the scalar. So you get something like this. Okay, and you can think of this to be m into okay, basically I can put a V here. It's Q dot V cross B into V, which will give me power, correct? And you know, this is like you don't know that much of vectors or anything, so this is like V B V. You know, you can write it like this, and when the V in that, the answer will be 0. This will return. You would have learned determinants. So this is dot product and a cross product. So you have two lines to be same. This is also velocity, two rows to be the same. The answer will be 0 in a determinant. You know that the 3 by 3 matrices, two rows are same or two columns are same. Like this is also velocity, this is also velocity, same magnitude. So you can subtract and you'll end up getting 0 on expansion of the determinant. So therefore the power itself becomes 0, and therefore I can write here on dv by dt into v itself will be 0. Okay, so I'm going to differentiate this. Differentiate this, which is m into. If I differentiate d by dt of v dot v, okay. So it's modular v into dv by dt plus v into again dv by dt only, and this is equal to 0. So d by dt of v dot v. d by dt. This is nothing but a v dot v, because m has been taken out common. This becomes 0. So when you differentiate something and you get it 0, this has got to be a constant. This has got to be a constant, correct? And I'm taking the m inside, it will be mv square. d by dt of mv square is equal to 0, which means this has got to be a constant, because differentiation of only a constant is 0. You can always divide it by 2 because it's only a constant. So you can just, it's dividing both sides by 2. It doesn't matter. So you'll have 1 by 2 out still, and this will be half mv square. Therefore, this will become d by dt of half mv square is equal to 0. Thus we conclude that this energy becomes a constant. It's very, very complicated derivation. I'm not sure if it's there in your textbook, but if it's there, this is there in Aurora, to show that the work done by the magnetic field on a charged particle is 0. So work done is 0 means energy is 0. So that's what we are trying to prove. And how did we prove? It was quite complicated. You know the Lorentz force is Q dot V cross B, but we are not writing Lorentz force, we are writing power. There is Lorentz force dot V. And you know that V cross B dot V is like doing a determinant between velocity in one line, magnetic field in other line, velocity in one line. So if you have two rows to be the same, the determinant value is equal to 0. Okay, so you'll automatically get it as 0, and therefore I wrote it as 0. The power is 0. So just come back here and just say F is equal to m into A is dV by dt. So then power is now using this m into dV by dt into V, dot V in other words. So that is m into V dot V. And I'm going to do m into d by dt of V dot V vector. I'm going to product rule, I'm going to apply product rule u dot V, but it's actually between V and V only. So V into dV by dt plus V into dV by dt is equal to 0. Which is differentiation of V dot V. So you can always divide both sides by 2, doesn't matter. And then take the m inside, you get half mv square is equal to 0, which shows that only a constant's differentiation is equal to 0. Therefore, the energy is a constant. So you can say that I need not have actually differentiated here. It's an unnecessary. I could have just kept it like that and also proceeded. I don't know why Aurora has done this. This is quite unnecessary. You can just take it from here, m d by dt dot v dot v, because power is force dot velocity is equal to 0. So divide both sides by 2 and take the m by 2 inside. So you still get d by dt of half mv square is equal to 0, making the energy to be a constant, because differentiation of only a constant is 0. This is quite unnecessary according to me. Let's make it much more simpler by not doing it. Okay, so make sure you correct that part. Okay, next is let's talk about two parallel conducting wires. Okay, so let's talk about the force because of two parallel conducting wires. Force due to two parallel conducting wires carrying current. This is important. The previous expression, this is not so important. If you want, you can skip this. Not so important. Not so important. Okay, just an extra point that I covered. Okay, so the force due to parallel wires. Okay, let's draw two parallel wires here carrying current. You know the current carrying conductor produces a magnetic field. So then let's call this as I1 and let's call this as I2. Okay, the current due to the I1 will have a magnetic field B1, and that B1 will be inward. If you use right hand thumb rule, you know it will be pointing inward, and so I'm going to put the magnetic field B1 here. At this point, incidentally, it is B1, it is inward. Okay, the current I2, the second current, is going to produce a magnetic field, and that will be outward. At this point, if you see, it will be outward. That will be V2. So you have a current and V, and you know that to find the force, okay, Um, okay. Magnetic field is over. According to Fleming's left hand rule, how will the force be? The force will be like in this direction. And for here the force will be in this direction. That is the force on 1 due to 2 and the force on 2 due to the first wire. Force on the first wire due to the second wire. And that the second wire means magnetic field produced by the second wire. And the force on the second wire due to first wire, the directions are like this, considering Fleming's left hand rule. So you can write that using Fleming's left hand rule. You can keep Fleming's left hand rule and see your if your middle finger is pointing in the direction of the current. Yeah, and your index finger is the direction of the magnetic field. You will notice that you will obviously notice that you know the force is in this direction. It's hard for me to explain this in an online class, so I'm going to do one thing. Okay, to find the direction of force, that the force. Okay,